In this problem, we're asked to calculate the wavelength of a radio signal with a frequency of 100.7 megahertz. The speed of light, c, is a constant, 3.0 times 10 to the 8 meters per second, so we can use the following equation to calculate the wavelength lambda for the given frequency nu. In the equation, it relates nu to c over lambda, nu expressed in units of seconds to the minus 1. C, the speed of light, once again, is meters per second, sometimes expressed as meters times seconds to the minus 1 power. And the wavelength lambda must be expressed in meters in this equation. First, we'll use some basic algebra to rearrange that equation in order to solve for the wavelength. And when we do that, we find that wavelength in meters is equal to c divided by nu, speed of light divided by the frequency. Knowing that the unit for frequency is hertz, 1 hertz being equal to 1 second to the minus 1 power, or equivalent to one wave per second, and using the definition for the prefix mega, 1 megahertz being 10 to the 6th power hertz, or seconds to the minus 1, our conceptual plan for solving this problem becomes, first of all, converting megahertz, the frequency in megahertz, into a frequency in seconds to the minus 1 power. And then in a second step, we'll convert that frequency into a wavelength in meters using the equation at the top of the screen. So first, the conversion from megahertz to hertz is one. We'll use dimensional analysis for that, and we're just going to make use of the metric prefix mega. Converting megahertz into seconds to the minus 1 gives us 1.007 times 10 to the 8th power seconds to the minus 1 power. And then plugging that into our equation for lambda, along with the value for the speed of light, which is a constant, notice that the units cancel out to give us units of meters, which is consistent with a wavelength in meters. That gives us a wavelength of 2.98 meters.